Cancer's ionization energy, by the way. Anyway, moving on. All right. You have a nice break? One person? Good. Did you have a nice break? Good.
I worked on college apps.
Ooh, yuck. You wrote your essays? Yeah, what a bunch of bullcrap the essays are, right? They really are. You have to write them formally. And I don't know. Here's how lazy I was. I didn't write my application essays for Cornell or Columbia. And so one of the teachers found out, I don't know how, that I didn't write it. So they pulled me out of class and made me go to what was called the writing center of our school and made me write my essays for college. This was like the day before it was due. That's how lazy I was. So got into both schools though. Anyway.
Did you do anything for break, Mr. Burnett?
Did I do anything for break? Yeah, no. Not a thing. I didn't check my phone. I didn't check my emails. I didn't do nothing. Had family over. And I had one really good moment in a family conversation. This was with my baby brother, Michael. Now, Michael's in his 40s, so he's my baby brother. And he's got a little girl who's 7 years old, Harper. And my sister-in-law, Sarah, was complaining that, they were playing The Floor is Lava, right? You've all played that. The Floor is Lava, okay? We all know this game. And she was complaining that my brother Michael elbowed her and knocked her off the couch. Oh, he's just super competitive. I was like, he's not super competitive, Sarah. The floor is lava, all right? The floor is lava. And my brother Mike was like, thank you. Thank you for explaining it. And she was like, well, he pushed me. I was like, Sarah, the floor is lava. I would have pushed you too. Why? Because the floor is lava. So if you ever play Floor is Lava with a little kid, don't get upset if you knock them over or something. They cry or whatever. It's not a big deal. The floor is lava. It's either you or them. And I'm not stepping in the lava. So, Aditya, that was the highlight of my holiday break. That was my Christmas break moment. I was like, thank you. See, because the interaction between males and females, we are different. We are different. And from a male perspective, if the floor is lava, ladies, the floor is lava. And you have to reckon that. But anyway, boring crap from me. All right, let's move on with this stuff. We had left off talking about cyclic structures, and I did make a mistake on the nomenclature, so I want to go and clean that up. Fortunately, the mistake wasn't made with any of the examples that I gave you. That's coming up later. Okay. The rule is the size of the ring does make a difference. If the ring is smaller than the carbon chain that's attached to it, you name it as though it's an attachment. In other words, you could have a cyclopropyl attachment, or you could have a cyclobutyl attachment if the thing attached to the ring is really long. So let me show you an example. Suppose we had cyclobutane, and then attached to cyclobutane, we're going to have this carbon chain. Let's put a chlorine here, and then let's put something like that. The way this works is you compare the ring to the size of the alkane chain. The ring has 1, 2, 3, 4 carbons. However, the alkane chain has 1, 2, 3, 4, 5, 6, 7 carbons. So we're going to name this as though it's a heptane, not as a cyclic structure. So if the alkane chain is longer than the ring, then we use the alkane chain as the name. So the name of this compound is going to be 1-chloro, 2-cyclobutyl. Instead of cyclobutane, cyclobutyl, heptane. So I apologize for that mistake. I think I told you that it's always the ring. That's the most important thing. The thing is, It is almost always the ring, because if you have a large alkane chain attached to a cyclic structure like this, it's very unstable and it's very likely to fall apart. So you're not going to see a lot of these, but I did notice the mistake and I wanted to correct it. Questions, comments, concerns?
Mr. Burnett?
Yeah.
If both the chain and the ring are the same number of carbons, does it matter which one you name first?
Go with the ring as the parent name. That's a good question. Anything else? And apparently LibreText thinks that this is the most important thing in the world. It's like all those questions are about nomenclature, which I think the ring flip delta G calculations are more important, but from a thermodynamic point of view. What does that even mean from a thermodynamic point of view? I love to make things sound important. All right, going back to our little structure. We said that cyclic structures have two problems. One, we have something called angle strain. And in angle strain, we are dealing with the fact that the angle is not equal to 109.5. We want that 109.5 degree tetrahedral angle. So if we're dealing with a structure like cyclopropane, then this bond angle, theta, dude, that looked like a smiley face. That's the worst theta ever. With like a winky smiley face. Get rid of that. Is that theta? Dude, I'm losing my mind. Or is this theta? I am really having a senior moment. Which is theta?
The first one.
The top one.
The bond angle beta. See, that's what you do. If you don't know the words, then just choose something else. The bond angle beta here would be 60 degrees. So we have a really tight angle. The electrons are extremely crowded together, and we wind up with, again, this what we call Bayer strain, which is Bayer, which is the issue that the angles are too tight, and therefore we wind up with a lot of electron repulsion. You know, if we deal with a square, cyclobutane, then the bond angle is now 90 degrees, which is a little bit better, but still highly strained. Now, when you get to cyclopentane, now your bond angle is 108, which is very close. So you see a lot of cyclopentane structures in biology. You'll see, the ribose complex is actually a cyclopentane sugar. And cyclopentane you would expect to be pretty stable because of this 108 degree bond angle. The only one that hits 109.5 is cyclohexane. But here's the problem. If cyclohexane was flat planar, then the bond angle would be 120 degrees. But yet, when we look at cyclohexane, it comes out to be 109.5 degrees. You would think that the bigger an angle that you have, the better off you would be because it spreads out the electrons. And the answer is that's not correct. 109.5 is the best angle because if you're using a tetrahedron, all four things that are attached to the carbon go off in entirely different planes of direction. If you start getting a larger bond angle, the molecule flattens out and you wind up with eclipsing interactions. So the bigger the bond angle, the more eclipsing you get. And again, if we were using the molecule models, we'd be able to see this pretty easily. So if I was to draw cyclohexane as a flat plane, and I'll do the best I can here, then we would have two hydrogens attached to each carbon. 6 of the hydrogens would extend up from the carbons. And we would say that these 6 hydrogens represent the hydrogens that are on the top side of the ring. So green is going to be top side of ring. But we would also have 6 hydrogens that extend in the south direction, which represent the hydrogens that are on the bottom of the ring. Now, if we were to rotate this and look at this as a Newman projection, any of the 2 hydrogens that are adjacent to each other are eclipsed. So the question is, if we have eclipsing arrangements, we know that that creates a high amount of torsion stress. Right? We have that dihedral interaction between the 2 hydrogens, which are eclipsing each other. So this creates torsion stress, or how do we alleviate that? Well, the idea is to create something that is staggered. So how do we go from eclipsing to staggered? When we had an alkane, the hydrogen could just rotate around the carbon. They could do a 360-degree rotation, and we could rotate this in such a way that we could get a staggered arrangement, right? We could get that anti or gauche relationship, but it would be something that was staggered. The problem with a ring is you can't rotate the hydrogens freely, because as the hydrogens rotate and they bend towards the inside of the ring, they interfere with each other. So they can't rotate all the way around. If they rotate all the way around, it would break apart the ring. So what the ring does is it twists. And depending upon how it twists, we can move things out of each other's plane so that they wind up in a staggered relationship. So we wind up with 2 different types of strain. We said we had angle strain. The second one is torsion strain. By the way, angle strain is sometimes called ring strain, if we want to add that to our vocabulary. So we're going to take a look at torsion strain. And the torsion strain, again, is the difference between an eclipsing arrangement and a staggered arrangement. So the way a cyclic structure, by the way, there's one exception. Cyclopropane is the only flat planar ring. Every other ring does some sort of torsional twist. Now, there's an infinite number of twists that you can get, but the lowest energy twist is something called a chair conformer, or a chair configuration. So instead of having a rotamer where we're rotating around the carbon sigma bond, now we have a conformer, something where we're twisting, but we're not rotating the hydrogens. And they call it a chair conformer because it kind of looks like a chair with a headrest and a footrest, if you've ever seen one of those reclining chairs. So I'm going to draw it like this. We're going to take the left side of the ring, and we are going to bend the left side up. And then we're going to take the right side of the ring, and we're going to bend it down. So instead of being flat planar like this, the one side of the ring bends up, the other side of the ring twists down. So when that happens, and I'm just going to draw them as sticks, the hydrogens on the top side wind up doing this. The hydrogen on carbon number 1 is still pointing up, the way it was originally if it was flat planar. But the hydrogen on carbon number 2 now extends off, and still angles up, but it angles off at a tetrahedral angle. So when this goes to a chair conformer, we wind up with a 109.5 degree bond angle instead of a 120. Now, there's two ways that these hydrogens can split off. If they point straight up or down, we call this an axial hydrogen. And we've used the term axial and equatorial before at the beginning of the course when we were talking about expanded octets. If it bends away from the plane, then we call this equatorial. So when you bend these, and again, it would be really easy to see with the molecule models, when you bend these, instead of all of them being axial, like we had when this was flat planar, if we bend the ends of the molecule, some of them move into the equatorial position. So this third one is again pointing up axial, but the fourth one is now pointing up equatorial. The fifth one points up axial, and the sixth one points up equatorial. Notice that if it was in the up part of the ring, if it was on the top side of the ring, it still points up, but now only half of them are axial, the other half are now equatorial. So they have now moved off into two different directions. So they're not interfering with each other anymore. And that reduces the repulsion between the hydrogen charge clouds. With the bottom, axial down, remember, the bottom part of the ring is pointing down. Axial down, second one, equatorial down. Third one, axial down. Fourth one, equatorial down. Fifth one, axial down. Sixth one, equatorial down. So this reduces the torsion strain. Now there's still an interaction here that's problematic, right? If we look at these ones that I'm going to write H's in for, the hydrogens that are at carbons 1, 3, and 5 are all axial to each other, which means that they are eclipsing each other. So there is still an issue here, but it's a much lower energy issue than if cyclohexane was flat planar. Now there's two different chairs that you get, and they wind up in equilibrium with each other. Instead of bending the left side of the ring up, what if we bend the left side of the ring down? And instead of the right side being bent down, what if we bend it up? You don't get the same thing. So I'm going to draw a second version of this. We're going to take the right side and bend it up. And this time we're going to take the left side and bend it down. Before I do that, I'm going to number these carbons. Carbon number 1, 2, 3, 4, 5, and carbon number 6. Now, here's what people have trouble visualizing. And again, this is where the models would be so important. Let's say we're talking about the left side of the ring. We have it bent up in the first diagram. Now I'm going to bend it down. So if this is carbon number 1, when I bend it down, where does carbon number 1 move to in the second diagram? That's actually carbon number 1 right there. Are you following me? Again, I'm trying to pantomime it with my hands. In the first diagram, carbon number 1 is up here. And as we rotate it down, carbon number 1 winds up in that spot right there. So it looks like we took the molecule and twisted it. We didn't. We just bent it. Now, slowly visualize what's happening to the green hydrogen at carbon number 1. It's pointing up, right? But then as we bend this, what happens to it? Goes from axial to what? Actually, it only does this. Goes from axial to, well, there's only 2 choices there.
Equatorial.
There you go. It actually flips from axial to equatorial. So when we're drawing this, now it's still the top side of the ring. So it still points up, but it points up at an equatorial position rather than axial. And what about the red hydrogen that it was at carbon number 1? Originally it was axial, but it becomes equatorial. So let's go around the rest of the ring. 2, 3, 4, 5, and carbon number 6. So the one that was equatorial up is now axial up. The one that was axial up at 3 is now equatorial up. The one that was equatorial at 4 is now axial. The one that was equatorial or axial at 5 is now equatorial, and the one that was equatorial at 6 is now axial. So they have all flipped positions when you bent it into the other chair. And then the same thing with the bottom ones. We're going to go around the ring. Yes, the bottom ones all point down. So carbon number 2, this is now equatorial down. Carbon number 3, axial down. Carbon number 4, equatorial down. Carbon number 5, axial down. Carbon number 6, equatorial down. So now, if we're talking about cyclohexane and they're all hydrogens, these 2 structures are actually equivalent to each other. They have an equal number of hydrogens in the axial position. They have an equal number of hydrogens in the equatorial position. So we would expect a 50% of each of these to exist. 50% of the left chair, 50% of the right chair. We would have true equilibrium, right? An equal amount of equilibrium. So again, where are our problematic interactions? Well, they're at carbons number 1, 3, and 5. They're at carbons 2, 4, and 6. They're at wherever you have an axial interaction. So again, this interaction between these 2 hydrogens is problematic. But again, it's a much better configuration than what we had before. Now, the only thing that we did was we shifted the problem. So instead of there being an interaction at 4 and 6, now we have that same interaction where the hydrogens are at 1 and 5. So the question becomes, well, why is this important? Well, suppose we have something attached to the ring that's not hydrogen. Suppose we have something like, let's do 1-methyl cyclohexane. Are the 2 chair configurations equivalent? And I'm only going to draw where the methyl is. I'm not going to draw the hydrogens because the methyl group has a much larger charge cloud. So I'm going to draw my 2 chairs, right? I got bent up on the left, bent down on the right. And for the methyl group on this chair, I'm going to put the methyl group in the axial position. And then I'm going to draw the second version of this, where we have the right side now bent up and the left side bent down. So what happens to that methyl group that was axial? It becomes equatorial. That's right. So we put our CH3 pointing out in an equatorial position. Which of these two would be more stable? Well, where do we have the biggest problems? Axial or equatorial?
Axial.
Axial, Daniel. So which one would be more stable, the one on the left or the one on the right? And I emphasize the one on the right. And the answer rhymes with the word site. It's the one on the right. This one's more stable. So which one would dominate the equilibria? Well, it depends. At low temperatures, we would have more of the stable chair configuration. At high temperatures, we would have more of the unstable axial version. But nature tends towards stability. More often than not, we're going to have more of the stable chair configuration. So 1-methylcyclohexane will exist as both of these, but the more stable version will dominate. Now, why aren't equatorial interactions problematic? I'm sorry, does everybody have this configuration thing in gray at the bottom? Because I'm going to slide back in the show. All right. Let's look at our equatorial interaction here. Let's take a look at the equatorial interaction between carbon number 4 and carbon number 5. We have two equatorial hydrogens there. First of all, why are the axial hydrogens not a problem at 4 and 5? Are they eclipsed or staggered? If you look at the axial hydrogen on 4 and the axial hydrogen on 5, are they eclipsed or staggered?
Are they staggered?
They're staggered. And not only are they staggered, they're in the anti-position. You have the hydrogen at carbon 4 pointing north, and you have the hydrogen at carbon 5 pointing south, so they do not interact with each other at all. Take a look at the hydrogens on 4 and 5 that are equatorial. Why are they also not a problem, energetically speaking? They are also, okay, so the terminology, are they eclipsed or staggered? The equatorial ones at 4 and 5. Well, to being eclipsed, they have to point in the same direction. So the answer is staggered. Why are they staggered? Now they're both equatorial, so they're both pointing in the eastern equator, right? However, the green one is pointing up at a 109.5 degree angle, and the red one on carbon 4 is pointing down at a 109.5 degree angle. So they are actually going off in two completely separate, as a bird, two completely separate directions. So they're not in the same plane as each other. So equatorial interactions on things that are on neighboring carbons are never a problem because they alternate pointing up and pointing down. Equatorial up at carbon 5, equatorial down at carbon 4. Therefore, they're never in the same plane as each other. So therefore, they can never be eclipsing. So they are always going to be low energy, equatorial to equatorial. It's axial to axial where we get problems. Now, axial to axial between carbon 4 and 5 wasn't a problem because they were 180 degree different directions. But if you look at the hydrogen on carbon 2, it is axial north. The hydrogen at carbon 4 is axial north. They are eclipsing each other. The nice thing is they're separated by one carbon, but that's not a big enough separation. There is some torsional strain there. So axial, diaxial interactions are problematic. They're just not as problematic as if it was flat planar. So when we go back to our example for methyl, the two chair conformations, if the methyl is at carbon 1, it's either going to be axial or equatorial, depending upon how it bends. So the equatorial version is going to be lower in energy because it doesn't have any diaxial interactions. The problem with the first version is that that methyl group will interact with the hydrogen that's at carbon number 3. And again, tough to visualize. So there are some good videos, Khan Academy. He uses the models and shows you and everything. I would do the models right now for you, but I don't have the materials here. So I'm going to give you a chance to spend the last 20 minutes to start on watching the visualization. And I know I put a due date of the 10th on that, or at the end of this week or something like that. Go ahead and watch them tonight, because the next time I see you, none of this is going to make sense unless you can visualize it. There's also a little tutorial in your book on how to draw what I just drew there. I would check out that tutorial, because drawing it is half the battle. If you can draw it correctly, analyzing it is a lot easier. If you can't draw it correctly, then you're never going to get to the analysis point. Questions, comments, concerns before I have you go? It's not a hard concept once you can visualize it. It is hard based upon the crude drawings that I'm making for you. If you don't have any questions, then hey, go check out those videos and have a good afternoon. I'll see you on Thursday.